Sig test number 19 is fundamental theorem on a graph. So this notation here essentially is just saying that the function, the original function, capital F of x, equals the integral from 1 to x. So notice that we're starting here at 1. So I'm going to put a little star there so that we're notating that we're starting here at 1. From 1 to x. So we can go forwards to go to 2. If we go backwards, remember, we're going to get negative integral answers of little f of t dt. And this is a picture of little f of t dt. So the first one says, what is the integral from negative 1 to 1? So notice that negative 1 to 1, that's a smaller number on top and a bigger number on opposite, sorry. Smaller number on bottom, bigger number on top, which means that we're going to have a positive area. And so because of that, we're just going to add up the area between negative 1 and positive 1. So that's this yellow region right here. So from negative 1 to positive 1 is this yellow region. It has a base of 2 and a height of 1. So the area of that triangle would be 1/2 times base times height, which ends up being 1. So the integral from negative 1 to 1 of f of t dt would be 1. For this one, remember that anytime you have two functions being added or subtracted, you can split them up into two integrals. So I'm going to do two things. The first thing I'm going to do is fix this integral because it's from 0 to negative 1. We don't like it going that way. So I'm going to fix this graph and say that this is the integral from negative 1 to 0. I have to make it negative when I do that, of 2 plus f of w dw. So when I do that, let me just erase this down here to give me some more space. When I do that, now I'm going to split this up into two integrals. So I'm going to have the negative integral from negative 1 to 0 of 2 minus the integral from negative 1 to 0 of f of w dw. So let's do this one first because this is from the graph. The integral from negative 1 to 0, so that's this area right here. Alright, the area there has a base of 1 and a height of 1, so 1/2 times 1 times 1, since it's a triangle, would be 1/2. So I have minus 1/2, because the integral from negative 1 to 0 of f of w dw is 1/2, so minus 1/2. This one, remember that when we have a constant, it's like a rectangle function, so it has a height of 2, and then the base is 1, because the length from negative 1 to 0 is 1, so if I actually drew it out, I can draw it out like this. It's up here at a height of 2, and we're going from negative 1 to 0. So it's kind of like looking at this area here. So at a height of 2 and a base of 1, that gives me an area of 2 for that rectangle. So this is minus 2. So essentially I have negative 2 minus 1/2. That's negative 2.5 or negative 2.5. Next. This one wants to know f of 1. So now I'm actually plugging things back in up here again. So if f of 1 would be plugging in 1 right here. So the integral from 1 to 1, remember that's not going anywhere. So that's just a height. It doesn't have a base. So that would be 0. If I plug in 0, f of 0 would be from 1 to 0. Remember, we don't like that. So if I actually write it out, that would be the integral from 1 to 0 of f of t dt. And we don't like that. We don't like going from bigger numbers to smaller numbers. So if I flip it, it would be negative, and then the area from 0 to 1, is 1/2. So that's going to be negative 1/2. And then f prime of 1. Remember that when we're taking the derivative of the integral, all right, the derivative of the integral. So you can think of it like f prime of x equals d dx of the integral from 1 to x f of t dt. So remember, that's actually the second fundamental theorem of calculus. When you take the derivative of an integral, all you do is you take that variable and plug it into the function. So the derivative of capital F is actually f of x. So all I have to do is take 1 and plug it into this function. So essentially, what is f of 1? So I come over here to 1, and over here at 1, my actual function, the derivative function, actually equals 0. So f prime of 1 actually equals 0. So that's what we do using this graph for just the basic functions. Hopefully that made some sense. If you have questions about that, you can always school loop message me. So let me come down here to part 2 now. Part 2 says, now let v of t equal f of t. So this function, instead of being f of t, now we're going to call it the velocity function. So now it's v of t. It represents the velocity of a particle moving along the x-axis in centimeters per second. It says if the particle was 5 centimeters to the left of the origin at t equals 1 second, set up and evaluate an integral expression that will compute the following things. Now, first of all, it doesn't look like it doesn't look like much, but this is actually giving you an initial condition. So keep that in mind, that at t equals 1, the particle's already at 5 centimeters to the left of the origin. So if you actually think of left of the origin, that's a negative value. So let me change that to a negative 5. So that's the initial condition. 5 centimeters to the left would be 1 comma negative 5 is where its initial position is. So it says find the displacement of the particle between t equals 1 and t equals 2. So displacement, remember, is just where did it start, where did it end, and what's the distance between those two. So at t equals 1, we know that it's at negative 5, all right? And then at t equals 2, we need to find the position of that at t equals 2. So I literally need to, I need to look at how much area has accumulated between 1 and 2. Okay, so if I look at the area that's accumulated between 1 and 2, it has a base of 1 and a height of negative 1. So since this is a triangle, it's going to be 1/2 times 1 times 1. So the area of this triangle is negative 1/2. So the displacement of the particle between t equals 1 and t equals 2, it moved in the negative direction 1/2. So this is going to be negative 1/2 or negative 0.5 centimeters. So that's how much it changed. It changed 1/2 centimeter to the left. Total distance. Remember that total distance is not allowed to be negative. Okay, so between 1 and 2, it's not allowed to be negative down here. So I'm actually going to redraw this and make it positive. So total distance, we're looking at the absolute value. So let me get rid of that down there. So it's exactly the same shape, but now it's positive. So if it was a negative 1/2 before being below the x-axis, now it's going to be a positive 1/2 because it's above the x-axis. So when I write that for my total distance, it equals a positive 1/2. All right, so that's the total distance that I've traveled. It doesn't matter the direction I'm going in. I just want all of the distances added together. Oh, by the way, it did say to set up the integral as well. So let me write the integrals for these. For displacement, it's going to be the integral from 1 to 2 of v of t dt. And for total distance, it's going to be the integral from 1 to 2 of the absolute value of v of t dt. And then last but not least, it wants the actual position as a coordinate point at t equals 2. So this would be where it started. So remember we had this initial condition at negative 5. So I know that it starts at negative 5, and then we add the distance that it's accumulated between 1 and 2. So the distance from 1 to 2 of v of t dt is the distance that it's accumulated. So if it starts at negative 5, and then we already actually calculated this integral, that was the first part up here. So it traveled negative 0.5 to the left. So negative 5 minus 0.5, because it's moving further to the left, would be negative 5.5 centimeters. So that's its position at t equals 2. It started at negative 5, and then it moved an additional 0.5 to the left, and now it's at negative 5.5 centimeters. So hopefully that helps to explain the 19th SIG test a little bit. If you guys have questions, school at me.